Right now, you're sitting in a room. You think you see everything around you, walls, furniture, air. But you're wrong. There's something else in this room with you, something invisible. Something that passes through your body trillions of times per second. It's everywhere, holding galaxies together, bending spacetime, making up most of the mass in the universe. And we have absolutely no idea what it is. Welcome to the dark matter mystery, the greatest puzzle in modern physics. Everything you've ever seen, every star, every planet, every atom in your body, makes up less than 5% of the universe. 5%. The rest? 27% is dark matter. 68% is dark energy. Together, they make up 95% of everything that exists. And we can't see either of them. We can't touch them. We can't directly detect them. We only know they're there because without them, the universe wouldn't make sense. Galaxies would fly apart. The cosmos would collapse. Reality itself would be impossible. So let's talk about the invisible universe, the one that's been hiding in plain sight all along. In the 1930s, Swiss astronomer Fritz Zwicky was studying the Coma Cluster, a group of over 1,000 galaxies bound together by gravity. He measured how fast these galaxies were moving. Then he calculated how much mass would be needed to keep them gravitationally bound at those speeds. The answer shocked him. The visible matter, stars, gas, dust, accounted for less than 1% of the mass required. The galaxies were moving so fast they should have been flung apart billions of years ago. But they weren't. Something invisible was holding them together. Zwicky called it dunkle Materie, dark matter. Nobody believed him. For decades, his discovery was ignored, dismissed as an error, a miscalculation. But Zwicky was right. He just couldn't prove it yet. In the 1970s, astronomer Vera Rubin provided the evidence that would change everything. She studied the rotation curves of spiral galaxies, measuring how fast stars orbit around the galactic center at different distances. According to Newton's laws, stars farther from the center should orbit more slowly, just like planets in our solar system. Mercury orbits the Sun faster than Neptune because it's closer and feels stronger gravity. The same should apply to galaxies. But that's not what Rubin found. Stars at the edge of galaxies were moving just as fast as stars near the center. Some were even moving faster. This shouldn't be possible, unless there's more mass than we can see. A lot more mass. Rubin calculated that galaxies must contain 6 times more dark matter than visible matter. 6 times. And it's distributed in a massive halo surrounding each galaxy, extending far beyond the visible stars. This was revolutionary and terrifying, because it meant that everything we thought we knew about the universe was based on a tiny sliver of reality. We'd been studying the foam on the ocean, thinking it was the whole sea. But here's the strangest part. Dark matter doesn't just fill space randomly. It forms a cosmic web, a vast network of filaments stretching across hundreds of millions of light years, with galaxies forming along the strands like dew on a spider's web. Simulations show that without dark matter, galaxies wouldn't exist. The early universe was too smooth, too uniform. Tiny quantum fluctuations after the Big Bang wouldn't have had enough gravitational pull to collapse into stars and galaxies. But dark matter acted as scaffolding. Its gravity pulled normal matter together, creating the structure we see today. We are living inside dark matter's architecture. Our existence depends on something we can't see. So what is dark matter? That's the trillion-dollar question. The truth is, we don't know, but we have theories, lots of them. The leading candidate is called WIMPs, weakly interacting massive particles. The idea is that dark matter is made of particles that have mass and gravity but don't interact with light or electromagnetic forces. They pass through normal matter like ghosts. You could have 1 trillion dark matter particles passing through your hand right now, and you'd never feel them. They don't collide. They don't absorb energy. They just drift through everything. If WIMPs exist, they'd be left over from the Big Bang, relics from when the universe was a hot, dense soup of particles. As the universe expanded and cooled, most exotic particles annihilated each other. But WIMPs would have been just stable enough to survive, and because they barely interact with anything, they'd still be here, making up the invisible majority of mass in the cosmos. Scientists have built detectors deep underground to catch them. Places like the Large Hadron Collider try to create them. Observatories scan the sky for signs of WIMP annihilation, flashes of gamma rays that might signal dark matter particles colliding and destroying each other. But so far, nothing. Decades of searching, billions of dollars spent, and we haven't detected a single WIMP, which means either they're even harder to detect than we thought, or we're looking for the wrong thing. Some physicists are starting to lose faith in WIMPs, so what else could dark matter be? Another candidate is Axions, hypothetical particles that are much lighter than WIMPs, but incredibly abundant. If Axions exist, there could be trillions passing through every cubic centimeter of space. They'd be so light and weakly interacting that detecting them would require entirely different technology. Experiments like ADMX, the Axion dark matter experiment, use powerful magnets and ultra-sensitive detectors to look for the faint signal of axions converting into photons. It's like trying to hear a whisper in a hurricane. But if axions are real, they could solve multiple problems at once, not just dark matter, but also mysteries in particle physics. Still, we haven't found them either. Then there are more exotic ideas. Primordial black holes, tiny black holes formed in the early universe, not from collapsing stars, but from density fluctuations right after the Big Bang. They could be microscopic, or the size of asteroids, or anything in between. They'd have mass, they'd exert gravity, they'd be invisible because they're black holes. But recent observations suggest they can't account for all dark matter. There just aren't enough of them. Some physicists propose sterile neutrinos, ghostly particles that barely interact with anything, even less than regular neutrinos, which already pass through entire planets without touching a single atom. Others suggest dark matter isn't particles at all, but modified gravity. Maybe Einstein's equations break down on galactic scales. Maybe gravity behaves differently than we think when you're dealing with vast distances and immense masses. This theory is called MOND, Modified Newtonian Dynamics. It can explain some galactic rotation curves without invoking dark matter, but it struggles with other observations, like gravitational lensing and the cosmic microwave background. Most physicists think MOND is wrong, but a few still defend it, because the alternative, that 95% of the universe is invisible, is almost too strange to accept. Let's talk about gravitational lensing. This is one of the most compelling pieces of evidence for dark matter. Einstein's general relativity predicts that massive objects bend spacetime, and light follows those curves. So when light from a distant galaxy passes near a massive object, like a galaxy cluster, the light gets bent, creating distorted, magnified images. We can measure how much bending occurs and calculate how much mass is causing it. And here's the kicker. The amount of bending is always greater than the visible mass can account for, sometimes much greater. In 2006, astronomers observed the Bullet Cluster, 2 galaxy clusters that had collided and passed through each other. The visible matter, hot gas, was slowed down by the collision and got left behind in the middle. But the gravitational lensing maps showed that most of the mass wasn't where the visible matter was. It had passed right through, unaffected by the collision. That's exactly what you'd expect if dark matter exists and doesn't interact with normal matter. The Bullet Cluster is smoking gun evidence. It's almost impossible to explain without dark matter. Then there's the cosmic microwave background, the afterglow of the Big Bang, a faint radiation that fills the entire universe. Tiny fluctuations in this radiation tell us about the density and composition of the early universe, and the data matches predictions perfectly if you include dark matter. The ratios of ordinary matter, dark matter, and dark energy that produce the observed cosmic microwave background pattern are incredibly specific. Change them even slightly, and the pattern wouldn't match. This is independent confirmation. Dark matter isn't just needed to explain galaxies, it's needed to explain the entire history of the cosmos. But here's the frustrating part. We can map dark matter. We can measure its effects. We can simulate how it behaves. But we can't touch it. We can't capture it. We can't bring it into a lab and study it. It's like knowing a ghost is in your house because doors open and close, but never seeing the ghost itself. And it gets weirder. Dark matter doesn't just surround galaxies, it's inside them. Right now, as you're reading this, dark matter particles are passing through Earth, through you, millions of them every second. Some estimates say that in your entire lifetime, maybe one dark matter particle will actually collide with an atom in your body. 1. Out of trillions. That's how weakly they interact. You are mostly empty space. And the invisible matter passing through you is even more ghostly than the atoms you're made of. Some scientists propose that dark matter might have its own complex physics, dark atoms, dark molecules, even dark chemistry. Maybe there's an entire dark sector of particles interacting with each other in ways we can't see, forming structures parallel to our own. Dark planets, dark stars. Dark life? Probably not. Because for complex structures to form, you need interactions. Particles that stick together, transfer energy, emit light. Dark matter doesn't do any of that, as far as we know. It's gravitationally bound, but otherwise inert. A shadow universe sharing the same space as ours, but never touching. Still, the possibility is tantalizing. What if we're not alone? What if there's another form of matter-based existence right here, invisible to us, and we're invisible to them? Now let's talk about dark energy, because dark matter isn't the only mystery. In 1998, astronomers studying distant supernovae made a shocking discovery. The universe isn't just expanding, it's accelerating. Galaxies are moving away from each other faster and faster. This shouldn't happen. Gravity should be slowing the expansion down. But something is pushing everything apart. Something with negative pressure. Something that makes up 68% of the universe. We call it dark energy. And we understand it even less than dark matter. The leading explanation is the cosmological constant, a property of space itself. Einstein actually predicted this in 1917, then called it his biggest blunder, when he thought the universe was static. Turns out he was right the first time. Space has energy, and as space expands, more space is created, bringing more energy with it. This energy drives the acceleration. It's a property of the vacuum. Empty space isn't empty. It's seething with quantum fluctuations, virtual particles popping in and out of existence. Maybe dark energy is the cumulative effect of all that quantum activity. But when physicists calculate how much energy the quantum vacuum should have, they get a number that's 10 to the 120 times larger than what we observe. That's not just wrong, it's the worst prediction in the history of science. So either our calculations are catastrophically off, or something is canceling out most of the vacuum energy, leaving just a tiny residual amount. We don't know what. We don't know why. Another theory is quintessence, a dynamic energy field that changes over time, unlike the cosmological constant, which is static. If quintessence exists, dark energy might not be constant. It could get stronger or weaker as the universe evolves. This has terrifying implications. If dark energy keeps increasing, the universe could end in a big rip, where the acceleration becomes so strong that it tears apart galaxies, stars, planets, atoms, and eventually spacetime itself. Everything would be shredded. Or if dark energy decreases, gravity might win, causing a big crunch, the universe collapsing back into a singularity. Or maybe dark energy stays constant, and the universe expands forever, becoming colder, darker, and emptier until the last stars burn out and even black holes evaporate. The heat death, eternal darkness. These are the ultimate fates cosmologists seriously discuss, and all of them depend on dark energy, something we can measure but not explain. Here's the most unsettling part. Dark matter and dark energy dominate the universe, but they don't interact with each other. Dark matter clumps together, forming structure. Dark energy pushes everything apart, resisting structure. They're opposing forces, and their balance determines the fate of everything. If there were slightly more dark matter, the universe would have collapsed billions of years ago. If there were slightly more dark energy, galaxies never would have formed. The ratio is finely tuned. Why? Is it coincidence, design, anthropic principle? We exist because if the ratios were different, we wouldn't be here to ask the question. Nobody knows. What we do know is this. We live in a universe where 95% of reality is invisible, where the forces shaping existence are beyond our current understanding, where the matter we're made of, the stuff of stars, planets, and life, is a tiny minority, a cosmic afterthought. Some physicists find this humbling, others find it infuriating, because it means that despite centuries of progress, despite quantum mechanics and relativity, despite sending probes to the edge of the solar system and detecting gravitational waves from colliding black holes, we still don't understand the most basic question. What is the universe made of? It's like discovering you've been living in a house your whole life, but 95% of the rooms are locked, and you don't have the key. You can hear sounds behind the doors. You can feel drafts. You know something is there, but you can't see it, and you don't know if you ever will. And yet, scientists keep searching. New detectors are being built, more sensitive experiments, better telescopes. The James Webb Space Telescope is mapping the early universe, looking for clues about how dark matter shaped the first galaxies. The Large Hadron Collider continues smashing particles, hoping to create dark matter in the lab. Underground experiments deep in mines and mountains wait patiently for a dark matter particle to finally reveal itself. Maybe we'll find it tomorrow. Maybe it'll take another century. Or maybe, just maybe, we're asking the wrong questions. Maybe dark matter and dark energy are symptoms of something deeper. A flaw in our understanding of spacetime. A missing piece in the laws of physics. A reality far stranger than we've imagined. What we do know is this. The universe is not what it seems. The light we see, the matter we touch, the forces we experience. They're just the surface. Beneath it all is an invisible ocean, a dark cosmos, and we are floating on a thin raft of atoms, surrounded by mystery. So the next time you look up at the night sky and see stars, remember, you're seeing less than 5% of what's out there. The rest is hidden, waiting, holding galaxies together, tearing the universe apart, passing through you right now. And we have no idea what it is. Welcome to the dark universe. It's bigger, stranger, and more mysterious than anything we ever imagined. And it's the only universe we've got.